Fan of this got tissues. Alright, it's a Sunday. I'm back.
Snake, long face in the bank, short change. This toy would feel like 40 steaks while we go home patrol the gate. What's going on? I'm in a bar with the Jordan face. High as hell, keep the Reggie off of 70 or wedding cake. 10 Cressy chair, heavily the blessings came. Might stretch a bit but never came. On the Benz barricades, blood-stained messages I never sent. My brain left, see what's left. On the left, etch a sketch when I live, shivering. Erasing what I did, opaque. Be complacent as the wind, my brother like sunrise. We all need you, Godspeed you. Black Emperor, Dark Legions. What's the rundown? Lump sums a piece of some and guns now. And let me hit the split before that bitch run out. I heard it's up to us more than enough. I know I'm playing a tough crowd. Convert the day to turn our races to whip the bus round. We about to shake the taco truck down. Now I'm playing, play the couple like a bus down. I'm all a brand saying.
When I found out my friend got a great deal on a designer dress from Winners, I started.
All right. I don't know if I'm actually gonna watch that thing, but yeah. Vibe coding 101, prompt engineering. All right, so yeah, I do want to try read this for a bit. Oh, I already had this downloaded. We're gonna put that up there. Exit out of this. Put this as a just trying to clean up shop here. We're gonna close that. That's fail. You exceeded your, yeah, see, I don't think that's the case, actually. I don't think I exceeded I don't think I exceeded my thing at all. I don't know how that could be the case. Let's see. close this down. Okay, we have our IDE. We have the textbook that we want to try to read a bit. I do have a basketball game over here that I'm like loosely watching, although I don't know if that's making me the most productive. But I'm not super concerned with that because it is Easter Sunday, so I don't necessarily think today is like a huge work day. There's some basketball on, watching
On TSN.
Yeah, Easter Sunday. We have some friends coming over for dinner tonight, so probably won't be a very long stream for me. I do know I'm gonna be required to clean up. So yeah, let's see what we can get done. I think if we can figure out this OpenAI API issue with the limits and whatnot, then we'll be fine. Um, yeah, that's the plan today. Let's put something on just to have it there. I'm not really sure how we've spent so much on this already. Doesn't really make sense to me. I'm not sure what's actually calling it to make it run like that. So um waterfalls, that is something um let's see, yeah, let's take a look at this waterfalls. Creating a waterfall using pre-built waterfalls. Okay, so waterfalls allow you to utilize multiple data points in a predetermined sequence so you don't duplicate tasks or spend extra credits. Using a pre-built waterfall. Let's take a look at this waterfall thing that was talking about. Get rid of that. Auto import shares template. Monitor for job changes. What does it say? Edit. Go to parent column. Duplicate, hide. Edit column. I want to make sure this isn't run settings. Auto update is, well, yeah. I don't want this to auto update. I think that might be what's causing the issue there with all the running of stuff. We're gonna try run this. See if that works. I am curious how much that's costing us as well. Save tasks, how to manage memory. How to manage memory Apify. Increase memory control issues, how to optimize speed. Did that run? I kind of feel like it didn't. Oh yeah, let's check out this. What is trying to do that? Let's check out this. Do a check-in. 463 views. $32. 8 subscribers. Yeah, we're not doing numbers right now. These are relatively static, so we're gonna trade sideways right now. This timed out, eh? Okay. I don't understand how there could be 8 gigabytes of data. I don't think that's... Okay. I'm gonna delete that one. Confirm delete. And this one is BF Dentistry. Okay. This one is Edgemont. This one is Edgemont as well. So we're gonna delete this one. It's weird this is gonna run this game.
In a playoff game, if this were a boxing match, the ref would.
This game doesn't want to watch. This doesn't want to play the game. Oh well. BRB, guys. Alright. Switching chairs. You call me? What's up? Huh? Can I go to the store? Said, can I go to the store? For what? All right, team. Unfortunately, I've been called to duty. What was I gonna say? I'll put something on. Um, um,
Hey everyone, today we're diving into the book AI Engineering by Chip Wynn. 800 pages of really great content about this in-demand field that's offering salaries of $300,000 or more. In this video, I'm summarizing everything from the book to help you get a high-level overview of the field. We'll talk about foundation models, prompt engineering, RAG, fine-tuning, agents, how to build a system, improving inference, and more. I also want to mention, this is a super high-level overview of a very detailed technical book. Don't expect to learn all the details just from watching this video. I really recommend using this as a way to get an overview of what the field looks like and use it as a jumping off point for your own research and exploration. So what exactly is AI engineering, and how is it different from traditional machine learning? Let's break it down. AI engineering has exploded recently for two simple reasons. AI models have gotten dramatically better at solving real problems, while the barrier to building with them has gotten much lower. This perfect storm has created one of the fastest growing engineering disciplines today. At its core, AI engineering is about building applications on top of foundation models, those massive AI systems trained by companies like OpenAI or Google. Unlike traditional machine learning engineers who build models from scratch, AI engineers leverage existing ones, focusing less on training and more on adaptation. These foundation models work through a process called self-supervision. Instead of requiring humans to painstakingly label data, these models can learn by predicting parts of their input data. This breakthrough solved the data labeling bottleneck that held back AI for years. As these models scaled up with more data and computing power, they evolved from simple language models to what we now call large language models, or LLMs. And they didn't stop there. They've expanded to handle multiple types of data, including images and video, often becoming large multimodal models. Nowadays, we're seeing foundation models power everything from coding assistants like GitHub Copilot to image generation tools, writing aids, customer support bots, and sophisticated data analysis systems. Now that we've covered what AI engineering is, let's dig deeper into foundation models themselves, how they're trained, how they work, and why understanding their architecture matters for AI engineers. Foundation models at their core can only know what they've been trained on. This might seem obvious, but it has profound implications. If a model hasn't seen examples of a specific language or concept during training, it simply won't have that knowledge. Most large foundation models are trained on web-crawled data, which brings some inherent problems. This data often contains clickbait, misinformation, toxic content, and fake news. To combat this, teams use various filtering techniques. For instance, OpenAI only used Reddit links with at least 3 upvotes when training GPT-2. The language distribution in training data is also heavily skewed. About half of all crawled data is in English, which means languages with millions of speakers are often underrepresented. This is why specialized models for specific languages and domains are becoming increasingly important. Also, the distribution of domains in one of the main training datasets leans heavily towards business, tech, news, and art. In terms of model architecture, most foundation models use transformer architectures based on the attention mechanism. But to understand why transformers were such a breakthrough, we need to look at what came before. Transformers were invented to solve the problems of sequence-to-sequence models, which used recurrent neural networks for tasks like translation. These had 2 main components: an encoder that processes inputs and a decoder that generates outputs. Both worked sequentially, token by token. The problem is that the decoder only has access to a compressed representation of the entire input. Imagine trying to answer detailed questions about a book when all you have is a brief summary. Also, input processing and output generation are done sequentially, so it's slow for long sequences. Transformers solved this with the attention mechanism, which allows the model to weigh the importance of different input tokens when generating each output token. It's like being able to reference any page in the book while answering questions. Plus, transformers can process input tokens in parallel, making them much faster. During inference, transformers work in 2 steps. First, prefill. Process all the input tokens in parallel to create the intermediate state. And second, decode. Generate 1 output token at a time. The attention mechanism uses 3 types of vectors. First, query vectors. These represent what information the model is looking for. Next, key vectors, like indices of previous tokens. And finally, value vectors, the actual content of the previous tokens. The model computes how much attention to give each input token by comparing the Q and K vectors. A high similarity score means that the token's content, V, will heavily influence the output. This is why longer context windows are computationally expensive. More tokens mean more K and V vectors to compute and store. Attention is almost always multi-headed, allowing the model to focus on different groups of tokens simultaneously. In Llama 2.7b, there are 32 attention heads, for example. A complete transformer consists of multiple transformer blocks, each containing an attention module and a neural network module. The number of blocks is often called the number of layers. Before and after each block, there's an embedding module that converts tokens and their positions into vectors, and finally an unembedding layer that maps output vectors to token probabilities. So that's a super high look at this. I would really recommend either reading the book or check out StatQuest for an awesome overview of transformers and the attention mechanism. I'll link that in the description. That's really how I learned. While transformers dominate, they're not the only architecture. Models like RWKV, which combines RNN-based approaches with parallelization capabilities, are gaining traction for certain applications. In general, larger models with more parameters have greater capacity to learn and perform better. The number of parameters helps us estimate the compute resources needed for training and inference as well. However, note that parameter count can be misleading with sparse models, so those with many zeros, which can be more efficient. A large sparse model might require less compute than a smaller dense one. When designing models, compute is often the limiting factor. The chinchilla scaling law helps calculate the optimal model size and data size for a given compute budget. It suggests that the number of training tokens should be about 20 times the model size, so a 3 billion parameter model needs about 60 billion training tokens. While the cost for achieving the same model performance is decreasing over time, the cost for improvements remains high. Going from a 3% to a 2% error rate might require an order of magnitude more data, compute, or energy. But even small performance improvements can make a huge difference for downstream applications. As we keep scaling models, we're approaching two significant bottlenecks. First, training data. There's concern we'll run out of high-quality internet data in the next few years, forcing models to train on AI-generated content, potentially causing performance degradation, or requiring access to proprietary data like copyrighted books and medical records. Second, electricity. Data centers already consume 1 to 2% of global electricity, limiting how much larger they can grow without significant energy breakthroughs. Pre-trained foundation models face two main issues. They're optimized for text completion, not conversation, and their outputs can be factually incorrect or ethically problematic. Post-training aims to address these issues through two main steps. First, supervised fine-tuning. Supervised fine-tuning optimizes the model for conversations instead of completion. This requires high-quality instruction data, showing the kinds of requests the model should handle and how it should respond. It's essentially teaching the model what good responses look like. Second, preference fine-tuning. Preference fine-tuning aligns the model with human values using reinforcement learning, often called reinforcement learning from human feedback. This involves training a reward model that scores outputs based on human preferences, and optimizing the foundation model to generate responses that maximize these scores. While reinforcement learning from human feedback has been the standard approach, newer methods like direct preference optimization, DPO, are gaining traction. Some companies even skip the reinforcement learning step entirely, instead generating multiple outputs and selecting those with high reward model scores. This is a strategy called best of n. Foundation models don't just produce a single definitive answer, they generate probabilities for possible outputs. How we sample from these probabilities dramatically affects the model's responses. The simplest approach is greedy sampling, always picking the highest probability token, but this leads to repetitive, predictable text. To introduce creativity, we use sampling techniques. Temperature controls how confident the model is in its predictions. Higher temperature values, like 0.7 to 1, make outputs more creative but potentially less accurate, while lower temperatures, close to 0, make outputs more deterministic and focused. Top K sampling restricts the model to choosing from only the K most likely next tokens, typically between 50 and 500, depending on how diverse you want the responses to be. Top P sampling selects the smallest set of tokens whose cumulative probability exceeds a threshold P. A value of 0.9 means the model will only consider tokens that together make up 90% of the probability mass. This probabilistic nature explains many of the behaviors we see in foundation models, like inconsistency with minor input changes and hallucinations where models confidently state incorrect information. Now that we understand foundation models a little more, let's talk about one of the most crucial yet underappreciated aspects of AI engineering, evaluation. For some applications, figuring out evaluation can consume the majority of your development effort. It's how you mitigate risks, uncover opportunities, and gain visibility into where your system is failing. Evaluating AI systems is significantly harder than traditional ML models for several reasons. First, the problems these models solve are often inherently complex. Evaluating a mathematical proof or the quality of a summary requires deep expertise. You might need to read an entire book just to judge if a summary captures the key points correctly. Second, tasks are typically open-ended with many possible correct responses. Unlike classification, where there's one right answer, a question like, "Write me a poem about resilience," has countless valid responses. Third, foundation models are black boxes. You can only evaluate them by observing their outputs, not by understanding their internal workings. Fourth, publicly available evaluation benchmarks quickly become saturated, which is when the model achieves perfect scores. What was a challenging test yesterday becomes an easy exercise today. And finally, for general purpose models, you need to evaluate not just known tasks, but discover new capabilities that might extend beyond human abilities. All of this is made worse by a general underinvestment in evaluation compared to model development. So let's start with some fundamental metrics used to evaluate language models during training. Most autoregressive language models are trained using cross-entropy, or its relative, perplexity. These metrics essentially measure how well the model predicts the next token in a sequence. Entropy measures how much information, on average, a token carries. The higher the entropy, the more information dense each token is, and the more unpredictable the language. If you can perfectly predict what I'll say next, what I say carries no new information. Language models learn the distribution of their training data. The better a model learns this distribution, the better it becomes at predicting what comes next, resulting in lower cross-entropy. A perfectly trained model would achieve cross-entropy equal to the entropy of the training data itself, and the KL divergence between the two will be 0. Perplexity is simply the exponential of cross-entropy. It measures the amount of uncertainty a model has when predicting the next token. Higher perplexity means that there are more possible options the model is considering. What counts as good perplexity depends entirely on the data. More structured data has lower expected perplexity because it's more predictable. The larger the vocabulary, the higher the perplexity because there are more possible options. And the longer the context length, the lower the perplexity tends to be. While perplexity is useful for guiding training and serves as a proxy for a model's general capabilities, it becomes less reliable for models that have undergone significant post-training with SFT or RLHF. As models get better at completing tasks, they might actually get worse at predicting the next token in a statistical sense. Perplexity can also be used to detect if a text was in a model's training data, because it would be unusually good at predicting those tokens, and to identify nonsensical text, which would have abnormally high perplexity. For some tasks, we can perform exact evaluation, where there's no ambiguity about the correct answer, like multiple choice questions. This is in contrast to subjective evaluation, like grading an essay. The gold standard here is functional correctness, evaluating whether the system performs its intended functionality. For example, if I ask a model to book a restaurant reservation, did it make the correct reservation? This is the ultimate metric for any application, though it's not always clear how to measure it. In coding tasks, functional correctness translates to execution accuracy. Does the code run and produce the expected output? For gaming bots, we can measure objective performance metrics like win rates. When reference data is available, we can evaluate outputs by comparing their similarity to this ground truth. This approach is bottlenecked by how much and how fast reference data can be generated, either by humans or AI. There are 3 main ways to compare outputs to references. First, exact match, a binary measure that works for simple questions with definitive answers, like who was the first woman to win the Nobel Prize? Second, lexical similarity, a continuous measure of how much the tokens overlap between the output and reference. This can use techniques like edit distance, how many changes are needed to transform one text into another, or n-gram overlap metrics like blue and rouge. The drawback is that you need a comprehensive set of reference responses, and the references themselves can be wrong. Plus, higher lexical similarity doesn't necessarily mean a better response. There are many ways to express the same idea. Third, semantic similarity. This is a continuous measure of whether 2 texts have the same meaning, regardless of the specific words used. This is typically implemented by comparing text embeddings using metrics like cosine similarity. The advantage is that it doesn't require references, but it does depend on the quality of the underlying embedding algorithm. One of the most powerful and common methods for evaluating AI models in production is using another AI model as a judge. These AI judges are fast, easy to use, and relatively cheap compared to human evaluators. They can work without reference data and can judge attributes like correctness, toxicity, hallucinations, and more. Studies have shown that AI judges can correlate strongly with human evaluators, sometimes showing higher agreement than between different human judges. They can also explain their decisions, which helps with transparency. You can use AI judges to score outputs, compare outputs to references, or pick the best of 2 responses. Since language models are generally better with text than numbers, AI judges tend to perform better with classification tasks than numerical scoring. When creating prompts for AI judges, you need to include the evaluation task, criteria, and scoring system. Few-shot examples generally work better than zero-shot, which we'll talk about later in the prompt engineering section, though longer prompts do increase costs. Interestingly, you don't always need your strongest model as the judge. Specialized, smaller models can often perform evaluation tasks effectively, which helps reduce costs and latency. However, of course, AI judges have limitations. Like all AI applications, they're probabilistic. The same judge given the same input can produce different scores if prompted differently or simply run twice. This makes evaluation results harder to reproduce or trust. Additionally, metrics aren't standardized across different systems. One system's definition of faithfulness might differ from another's. Models also exhibit biases. They might prefer responses from the same model. This is called self-bias. Favor the first answer in a comparison. This is position bias. Or prefer lengthier answers, verbosity bias. You can mitigate these biases through techniques like randomizing the order of responses, but this also increases costs. Now that we understand evaluation, let's tackle one of the most crucial decisions in AI engineering: model selection. With the increasing number of readily available foundation models, the challenge isn't developing models, but selecting the right one for your application. During application development, you'll go through model selection multiple times as you progress through different adaptation techniques. For instance, when doing prompt engineering, you might start with the strongest model to evaluate feasibility, then work backwards to see if smaller models would suffice. If you decide to fine-tune, you might start with a small model to test your code before moving to a larger one. The selection process typically involves two key steps. First, finding the best achievable performance on the task, and then second, mapping models along a cost-performance axis and choosing the model that gives the best performance for your budget. Your criteria for evaluating a model can be organized into 4 buckets. First, domain-specific capabilities. How well does the model understand your specific domain? For example, if you're